In the last video, we have seen the inverter and the AND gate. Today we will see the OR, NAND and NOR gates. So let's start. So first, what is the symbol representation of OR gate? This is the symbol representation of OR gate. Here there are number of input, can be any number. Here I have taken 2 input, but you can take any number of input. And this is the output, which is X, which is nothing but A plus B. So what is the truth table for this OR gate? This is input A, this is B, this is A plus B. Okay. If my inputs are 0, 0, then output is 0. 0, 1, 1, 0, 1, 1. Then for all cases, the output is high. It means my output will high output will high if any of my input is 1 or both are 1. You see, if any of my input is 1, then output is 1. Or if both are 1, then also my output is 1. So this is the truth table. Accordingly, you can write, if this is a 2 input, 1 is low, 1 is high, then what will be the output of this AND gate? Output of this OR gate, which is nothing but high. Okay, from this truth table you can write the operation. Now we will see how, after applying the waveform, how it is going to behave. Similarly, let's take a small waveform. Okay, this is 0, 1, 0, 1, 1, 0. Let's take another. This is 1, 0, 0, 1, 0, 0. 6, 6. Okay, these are the 2 inputs they applied to a OR gate. Then what will be the output? You see, when there 0, 1 means the output will 1. When both any of the input is high means output will high. Here also for this input is high means output will high. For the third interval, my both inputs are low, then my output will become low. For the fourth interval it is high, for the fifth interval it will again high, because this is high. And for the sixth interval, both inputs are low, means this is my output will become low. Okay, so for the first 2 interval and for the fifth and fourth interval, my output is high of this OR gate, and for the all other case my output is low. So this is applying this operation, applying this waveform. You can see when any of the waveform that is applied. Here I have written this 1, 0, 1, 0 for just for your convenience, but in your exam it might not written like 1, 0. From the signal you have to think whether it is 0 or it is 1. Okay, so this is the timing diagram. From this timing diagram you can see for this interval my signal is high, or for this interval my signal is low. Now we will see the some application of this one, in which cases this OR gate is we are going to use. Here I have taken 2 input. You can take any 3 input or 4 input. Accordingly my number of combination will change. For 3 input there will be 8 combinations: 0, 0, 0, 2, 1, 1, 1, 0, 0, 0, 2, 1, 1, 1. If I take 4 input, then there will be 16 combinations: 0, 0, 0, 0, 2, 1, 1, 1, 1. These are there are 16 combinations. So accordingly, number of input, my output will change. So let's take an example. Let's suppose this is a house. Okay, in your house there are 2 windows and 1 main gate. This is 1 main gate and there are 2 windows, and each of the window and main gate, they are connected to a OR gate. And at the output there is a alarm is connected. Okay, so what are the conditions that is there? If any of my window or door, these 2 window or any main door, if it will open, then it will give me a value high. It means it will become 1. Okay, suppose these 2 windows are closed and any theft that he or she came and he opened this main door, then it will give me a value 1. And these other 2 are closed, then they are 0, 0. Since it is a OR gate, any of the input 1 means the output will 1. And when the output will 1, the alarm will glow. Then you will come to know that yes, someone entered through this room. Okay, let's now second case. My door is closed, that is 0, or any of my window is, someone opened any of my window, then also I will get my output. And when I will get output 1, then my alarm will glow. Then you will come to know, okay, someone opened this window or this any door or window. And when my window and door is closed, means inputs are 0 0 0, then my output will be 0, then there will be no glow, no alarm. Okay, so this is one case that we can use our OR gate in our daily life. Now let's see, we can use this OR gate in our Boolean algebra. How? If you remember, in the AND gate we are doing that multiplication. AND gate represented by A dot B. It means 0 dot 0 is giving me 0, 0 dot 1, 1 dot 0, 1 dot 1. This is not 0 0 1. Okay, so this is nothing but Boolean multiplication. These are not binary multiplication. This is what Boolean multiplication. And this Boolean multiplication is same as my AND gate output. If you remember, what is my AND gate output for the two input A and B? For 0 0 0 1 1 0 1 1, what was my output? 0 0 0 1. This was the case. You see, this is the output of 0 0 0 1 of my AND gate, and this is from the Boolean multiplication. So you see, both are equal. It means my Boolean multiplication is same as AND operation. Now we will see for the OR gate. Okay, so similarly, this AND gate, this OR gate will do the addition of two numbers, 1 plus A plus B. It is represented as A plus B. X is nothing but A plus B. It will do the addition. So Boolean addition. So what is the rules for Boolean addition? Boolean addition means my 0 plus 0 will give me a value 0. 0 plus 1 will give me a value 1. 1 plus 1, 0 will give me a value 1. And 1 plus 1 will give me a value 1. So this is the rule for Boolean addition. Don't take it as 0, because 1 plus 1, if you what you remember in binary addition, 1 plus 1 means it is 1 0, means this sum is 0 and carry is 1. But here this is the Boolean representation, that we are representing a value 1 means a high value means that is 1. You see, this is nothing but 1, this is nothing but 1, this is nothing but 2. So I am taking all the 1 and 2, these high values, as my 1 label. And this is nothing but 0, which is nothing but my 0 label. Okay, so this is the Boolean addition. So you can check, my Boolean addition is same as my OR gate output. If you take, there are two input A, B, this is A plus B, 0 0 0 1 1 0 1 1. What is my output? 0 1 1 1. So this OR function output is same as my Boolean addition. Okay, this is the Boolean addition. This is the Boolean multiplication. So this Boolean multiplication is same as my AND operation, and this Boolean addition is same as my OR operation. Okay, so how to represent that? Like A plus B. If I have two input, then I will write X equal to A plus B. If I have three input, then I will write A plus B plus C. Okay. So this is how I represent my OR gate output. Now let's see the NAND gate. The next two, NAND and NOR, these two are called universal gate. This NAND and NOR, they are called universal gate. What do we know universal gate? Universal means I can use these two gates to form any gate. Means I can use my NAND gate to form NOT, to form OR, to form AND. Similarly, I can use my NOR gate. I can, using this NOR gate, I can form any number, any of these three gates. These are the basic gates. So I can form this basic gate from these two gates. That's why it is called universal NAND gate. Let's take a small example how a NAND gate can be used as a NOT gate. You see, this is, okay, first let me tell you, this is the representation of a NAND gate, symbol representation. This symbol representation, this is, let's take two input. There can be any number of input. Let's take two input A dot B. This is NAND. NAND means not AND. Okay, so this is the AND gate. At the output I am going to add one bubble. Bubble means it will form the operation of NOT. Then it will become A dot B whole bar. Okay, this bar is for this NOT. If you remember, if input is A, what is my output of inverter? It is nothing but A bar. Similarly, here my whatever the input A, B, output of this AND gate will become A dot B, and applying this bubble means it will give me a value A dot B bar. So this is the symbol representation of this NAND gate. Now let's see how this NAND gate can be used as NOT. Let's take this is a NAND gate. This is I am applying 1 over here. Okay. Since I have applied this 1, so there are these two are the input and it is the same. If it is 1, it is also 1. When my inputs are 1 to this AND gate, then what will become output? 1.1, it will give me value 1. This is the output of this AND gate. Since I applied a NOT, so it will convert my 1 into 0. So it will convert my 1 into 0 because of this NOT. Okay. Because here I am getting a value 1 at this point, and after applying this in bubble I am getting a output 0. So now you can see I am applying a 1 to this NAND gate and I am getting a 0, means it is performing the same function as inverter or NOT function. This NAND gate can be used to form NOT function. Similarly, this NAND gate can be used to form OR and AND, means at the output I will get A plus B. You see, this is the NAND gate, and again let's take this is the AB, and this is the output of a NAND gate, which is nothing but A dot B bar. As I said, this is the AND NOT, this is AND operation, this is not A dot B bar, and I am going to use this output into a inverter again, means again another NAND gate. So this is nothing but A dot B bar. Let's take this is as X. Let's take this is X. So it is X, it is X. So what will be my output? Output will become X bar. X dot X is nothing but X, and because of this bubble it will become X bar. Then what is my X? It is A plus B bar. Then again another bar is there, A bar. So this two bar, double bar means it will cancel out. It will give me a value A dot B. Okay. So remember this concept, when there is a double bar, it will automatically cancel out. It will give me a value simple A dot B. So this is the A dot B bar. When again it will act as a NOT gate. NOT gate means whatever the input, it will just invert the input. A dot B bar means it will become A dot B bar, again a bar. So this two bar will cancel out. It will give me a value AB. So if I take this point, I am applying AB at my input. What I am getting at my output is nothing but A dot B, which is nothing but a AND gate or not. AND gate, yes or no? So I can use my NAND and NOR both as NOT, OR and AND gate. Okay, that's why they are called universal gate. So this is the symbol representation of this NAND gate. Now easily you can say what is the truth table. Once you know the truth table for AND gate, you can easily say what is the truth table for NOT gate. If this is A, B, this is A dot B, this is A dot B bar. This is the output of this NAND gate. This is the output of the AND gate. So 0, 0, 0, 1, 1, 0, 1, 1. If you remember, for the AND gate, my output will become 1 when both input are 1. And for the other case, my output is 0. Okay. And for the NAND gate, what I have to do? I have to just take the invert. Means this value will become 1, 1, 1. This will become 0. This is the truth table for this NAND gate. It means when my both inputs are high, then my output of the NAND gate will become low. And if any of the input is 0, if this is 0, if this is 0, or this is 0, or both 0, if any of my input is 0, then my output will become 1. Okay. So this is the truth table for this NAND gate. So now easily you can do the operation using the waveform. Suppose this is a waveform given. Let's take 1, 0, 1, 1, 0. Let's take a 5 bit. And next one, let's take 1, 0, 0. Again 1, 1. Let's take this is a second bit. This is the AB2 input given to a NAND gate. So this is a NAND gate with a bubble and with a bubble. Okay. So what will my output? From the truth table you can see, when my both inputs are 1, then my output will be 0. That's why my output is 0. When my both inputs are 0, then my output, this is the output is 1. When any one of the input is also 0, this case or this case, then also my output is 1. When my both input again are 0, 1, again then my output will low. And when any of the input is 0 means output will 1. So this is the output of the NAND gate. Here you can see this 0 at the output. What does it indicating? It is indicating a active low output. it means at my output I am going to take the low values, active low values. They are the active component. They are the active values. Okay, since the bubble is there, these are the active components. Okay, so this is the operation, and similarly from this graph you can say the timing diagram. Let's take one example to understand one application of this NAND gate. Is this clear or not? Since here is bubble is there, that's why I am taking the active low values of the output. I am taking active low, not high values. I am taking active low. So let's take, here is one container, oil container. Here is one second oil container. Okay, and here is one sensor is present. Here is one sensor is present. From the sensor of the two oil container, I am taking the output. And here one LED is connected, LED, light emitting diode. Okay, so here it is, suppose any volt, 1 volt is given, any volt that is there. So what is the function of the sensor? When there is oil or field. Okay, when someone is drawing the oil from this container and the oil level, this oil level is below 1/4, or I can say below 25%. Equal to or below 25%, then the sensor will start working and it will give me a value 1. Okay, when the in the oil container, the oil present, which is 1/4 of the total container size. Let's take this is the 1/4. When this oil level decreased below this 1/4 or 25%, then my sensor will glow. My sensor will glow means it is nothing but 1. So similarly, this oil container will give me same. When this value is less than 1/4, it will give me a value 1. So what will be the output? 1.1 means 1, and again because of the bubble, it will give me a value 0. Because this is the NAND gate. When both inputs are 1, then my output will become 0. Okay. 0 means you can see now this LED, light emitting diode, this diode will glow. Means here it is the positive voltage connected to P side. This negative means less voltage connected to N side. Means it is forward bias. Forward bias means the diode will conduct current, and it will conduct means it will glow. It will glow. Let's take red light. Let's take red. So I have programmed in that way that once it will glow red means I will come to know that in both of my container, or in both container, my oil level decreased 1/4 or decreased 25%. Okay. Similarly, if I will connect a green LED over here, okay, and here it is 1 volt is connected. So what does it mean? Let's take a condition. This is ground. When this is a green LED is connected, suppose this oil is above 25%. It means this output is 0. This oil is below 25. Let's take this is below. If this is 1, this is 0, then what will be my output of here? Here the output will 0 because 1.0 is nothing but 0. And after the bubble means after this knot, it will become 1. If any of the input is 0 and another is 1, then what is the output of this and NAND gate is nothing but 1. 1 means this is 1 volt positive to P side and 0 volt connected to next side, means this LED will glow. When this LED will glow means it will glow green, means I will came to know that okay, any one LED, any of the container is more than 25%. No need to fill right now because one container is more than 25%. Which container is more than 25? This container is more than 25 because here the output is 0. 0 means this sensor is not glowing. Okay. When the sensor will glow, it will give, sensor will came to know that below 25 means it will give me a value 1. When it is more than or equal to 25, more than 25% means it will give me a value 0. That's why it is giving 0 means the oil is up to the mark. And similarly I am getting 1. 1 means this LED is glowing. LED glowing green means I came to know that okay, any container that is filled it is more than 25%. Okay, this is one application of this NAND gate. Now let's see how to express this NAND gate. This NAND gate, as I told, this is nothing but NOT and again AND. It is also called NOT plus AND. It is combined, give me a value NAND gate. I can use OR gate also to to form this NAND gate. How? Let's take these are the two input A and B, and I am going to use two bubbles at the input side, and I am going to use a NOT or OR gate. This is on symbol, circuit symbol of OR gate. Okay, so this output will give me A dot B. What it will become? It is nothing but it will give me value A dot B bar, means NAND gate output I will get. It is nothing but same as NAND gate. How? Here it is A. So after the bubble, what it will become? A bar. Here it is B. After the bubble, what it will become? B bar. Then this A bar, B bar, they are connected to the OR gate. This is the OR gate. So what will be the output? Output. What is the function of OR gate? A bar plus B bar. What are the two input applied to OR gate? That will simply add. So A bar plus B bar. We will see the De Morgan theorem. This is the De Morgan theorem. What it is said? It is said if A plus B bar, we can write it as A bar dot B bar. Means we can replace the bar with each term again. With changing the OR to AND or AND to OR. Means A dot B bar can be written as A bar plus B bar. Okay. Here the dot is replaced by plus, means AND is replaced by OR. Or I can say this AND, this OR is replaced by AND. But this whole bar is divided into both bar. Similarly, here the whole bar is divided into both bar. Okay. Now here I applied this A, here B. Because of these two bubbles present over here, they will invert my signal, that is A bar, B bar. And this OR gate, it will just add the two input A bar plus B bar. So A bar plus B bar, can I write A dot B whole bar? So I can write A dot B whole bar, which is nothing but my NAND gate. Okay, so the NAND gate can also be formed from using NOT and also from the OR gate also. Okay, by using the OR gate, I can also form OR gate with these bubbles before. Now let's see the NOR gate. So for NOR gate, let's see what is the symbol representation. NOR means NOT plus OR. So this is the OR gate, and in front of that I am going to add one bubble. That bubble will function the NOT function. So if this is A plus B, what will my output? This OR gate, this output will give me A plus B, and after the bubble I will get A plus B bar. So this is the output of this NOR gate. Okay, A plus B bar. This is the output of the OR gate only. But because of this bubble, it will taking the just one bar, that is A plus B bar. This is the output of NOR gate. So what is the truth table for this NOR gate? If you know the truth table of OR gate, you can easily find the truth table of NOR gate. If this is A, this is B, this is A plus B, this is A plus B bar. 0 0 0 1 1 0 1 1. Okay, so what is the output of this OR gate? My output will become 1 for each case, and when my output is 0, when my both inputs are 0. This is the output of OR gate. And now for the NOR gate, just take the inverse. 0 will become 1 and this 3 will become 0. Okay, this is the output of my NOR gate. It means my output of this NOR gate will become 1 when my both inputs are 0 or low. When my both inputs are low, then my output will become high. So this is the truth table. So based on the truth table, you can say when one input is low, one input is high, what will be the output? When one input is low, one is high, output will become low. So this is actually my output of this NOR gate. Output will become low. And when it is applied to NOR gate. Okay. Similarly, by using the waveform, you can also see. Let's take 1 0 1 1 0, and let's take 1 0 0 1 1 1 0 0 1 1, and it is applied to the NOR gate. Okay, this is the bubble indicating NOR gate. So for NOR gate, when my two inputs are 0, then only my output will become 1. So for only this instance, my output will become 1, and for all other case, my output will become 0. Are you getting or not? So for only when both inputs are 0, then only my output is 1, and for all other case, my output is 0. So this is using the waveform we can see, and from there you can see the timing diagram. So now let's see one application of this NOR gate, where we can use this NOR gate. This NOR is similar to NAND gate. That NAND is also called negative or. NAND is also called negative or. Negative or means before applying to the OR gate we are going to negate. Okay, that is the NAND gate. Similarly, the NOR gate that is said negative AND means this NOR gate can represent using NOT gate plus OR gate also. Also negative AND means if this is the two input A B, I am going to negate or negative this two input A dot B. Then I will take the AND gate. This is the negative AND. This is the negative symbol, the two bubbles, and this is the AND gate. So what will be the output? This is the A. So when A is applied to a bubble, it will become A bar. This B will become B bar. Then this A bar B bar applied to a AND gate. What will be the output? Output becomes just take the dot product. Means A bar dot B bar or the dot value or the multiplication we can say. Okay, this is the A B. Before bubble, after bubble this is nothing. I am just expanding this part, showing you how this after bubble it is becoming A bar and B bar, and after the AND gate it is becoming A bar dot B bar. Again from the De Morgan law, what do you know? A plus B bar is nothing but A bar dot B bar. This plus will replace by dot and bar will come to each input. So this A bar plus B bar can be written as A plus B whole bar, which is nothing but the output of my NOR gate. Okay, so this is the representation of a NOR gate by using two formula. One is using NOT and OR, and second one is the negative of AND. Okay, now let's take one example where we can use this NOR gate. Let's take here is one plane. Okay, here are the two wings. And here this plane is now on the sky. It is flying and it's supposed to land on the track. And here are some sensor. Here are some sensor. That sensor will glow when this there are wheels there. When they are extended means the wheels are hanged below means it is going to land. Then it will give me a value low. And when the extension is retarded means they are not extended, means the wheels that are not extended means it is retarded. It means it will give me a value high. So these three sensor for same. Here is one wheel is there. Here also one wheel, and here also one wheel is there below the aeroplane. And these three wheels will combine it when they will help this plane to land on the floor. Okay. And the three sensors they are applied to the inputs of an NOR gate. So this is the NOR gate. Okay, so when it is low, when it is extended, and when they are not extended means retarded, and then the output will become high. Okay, so here one sensor is one LED is connected that will glow. Now you see this LED, it is 1 volt is connected. This LED when it will glow, when the output is 0, when the output is 0, this output positive is connected to P side, negative voltage, that is less voltage connected to N side means this LED will glow red light. So when this output will 0, when any of my wheel that is not extended means that are retarded. If this is retarded means this will give me a value high. And let's take both these two wheels are extended and they are giving a value 0 0. So since this is a OR gate with a NOT means this is a NOR gate. So when any three inputs are any of the input is 1, then what will be my output? If you see the truth table of the NOR gate, so for 0 0 for the this is nothing but 1, for 1 for 0 1, for 1 0, for 1 1, this is nothing but 0. So this is the output of my NOR gate. I am not writing OR, directly I am writing NOR. It means if any of my input is 1, any of my input is 1 or both are 1, then the output is 0. Here you see, when this input is 1 means this sensor is sensing that this wheel is not retarded, not extended. It is retarded means that's why it is giving me a value 1. And when this any of the 1 means it will give me a value 0. 0 means this LED will glow. LED will glow means it will glow red means what does it mean? This LED is glowing red means any of the three sensors they are showing something, that is any of the wheels that are retarded. Okay, similar condition. here I can use one green LED. Okay, so this green LED will glow. This is grounded. If all the three wheels they are extended, means everyone is giving me a value 0. This wheel is extended, this wheel is extended, this wheel is also extended for landing. These three wheels are extended, this will give me a value 0. Extended means low. For each sensor, for each case, extended means low. I have programmed in that way that it will show me a value low for extended case. Then when three inputs are extended, then what is my output? Output will become 1. And when my output is 1, then this LED will glow green. I have used a green LED by using the wavelength, proper wavelength. This LED, when this is 1 means positive side connected to P side connected to positive voltage, N side connected to less voltage. So this LED will glow green. Green means now my plane is ready to land. Okay, this is by using the NOR. Similarly, I can use that negative AND also. This NOR gate represent this, one is this way and second one is negative AND. Okay, here the three inputs, one is here, and third one is here. These three same input. Now I am forgetting, just to forget this part. Now I am not using this OR and NOT. I am going to use this AND and negative of AND. Let's take any of the sensor. Let's remove this one, else you will confuse. Now let's take any of the sensor is giving me a value high. Means my any wheel is not extended. Let's take this wheel is not extended. That's why it will give me a value high. It means it is 1. And the rest are 0, 0. That is before the bubble. Before the bubble 0, 0, 1. After the bubble, what it will become? 1, 1, 0. Okay. 1, 1, 0, that is applied to the AND gate. So since any of the input is 0 to the AND gate, what will the AND gate will form? It will give me a value 0, because for the AND gate, any of the input 0 means it will give me a value 0. And 0 means now this diode will work. Because it is positive voltage, 1 volt connected to P side, 0 voltage to N side, this light will glow red. This light glow red means I will come to know that any of the wing or any of the wheel that is not extended. Okay, so I can use this symbol. I can use this symbol or this symbol. Any symbol we can use. Okay, so this is one example, or we can say one application that we can use our NOR gate. Next one is expression. So expression similar to NAND gate, we can here express our, suppose there are three input A, B, C. They are applied to a NOR gate. Here it is A plus B plus C whole bar. For 4 input A plus B plus C plus D whole bar. Okay. So this is that simple thing that is covered all the 4 gates, inverter, NAND or NAND NOR. In the next video we will see the exclusive OR and exclusive NOR, and we will do some problems, some numericals.